In this video, we're going to do a little reminder of the beginning of our booklet on reactivity series. So we're just going to go through a few of the reactions and I'll demonstrate on video some of the reactions of these metals, and we're going to look at it in terms of the reactivity. Now, metals, as we talked about, come in a variety of different types and have different ways in which they react and different abilities to react. So some are more reactive than others, and some will be obviously less reactive. And it means then that what we can do is we can form a little table with the most reactive at the top and the least reactive at the bottom. And that's what we call a reactivity series. It's a list of elements, usually metals, with the most reactive at the top and the least reactive at the bottom. And what we're going to do is we're going to just remind you first of all of how we put a reactivity series together. Now, we've seen these reactions a few times, so I'm not going to on the video show you these, but we'll talk over it. We'll get our basic reactivity, and then we'll talk about our competition reactions. And that's what I want you to do really in the worksheet, is to put these equations in. As you can see, if you look at the worksheet, there are equations to put in, so we'll talk through them here and then you can try them after you've watched the video. And then we'll look at our reactivity series, and then we'll look at how more reactive metals can steal from less reactive ones. So in terms of our reactivity series, we had a series of metals here and we looked at how they behaved when they reacted in air. And air contains oxygen, so quite often they talk about reacting with air, and what they're really talking about is reacting with oxygen. At the start of the year, you remember we saw copper. You heated it last year, and this year we saw that it increased in weight and mass whenever we heated. So copper, it didn't do very much. There wasn't a big spectacular reaction, but it changed from shiny brown metal to being dull and black. And what we found was, because it had on weight, it was combining with oxygen. Copper plus oxygen was turning into copper oxide. The other reaction we showed you was sodium. Now, when we brought sodium into the lab, it had to be covered in oil. It's such a reactive substance that we have to keep oxygen away from it normally. When we get rid of that oil and we heat, to get a really vigorous reaction and a yellow flame. Now, although that means that sodium's reacting much more quickly, and we're going to put it higher than copper in the reactivity series, it's basically the same reaction. The sodium was combining with oxygen from the air and turning into sodium oxide, but in a much quicker way, so it's more reactive. And then magnesium, again at the start of the year, we had looked at its reaction. It gives that brilliant white flame. So remember, every time you get magnesium reacting, you get that brilliant white flame, and then it leaves a white solid. Now, again, it's somewhere in between. It's not as vigorous as sodium, but it was more vigorous than copper. And again, it's behaving in the same way. Magnesium plus oxygen is giving us magnesium oxide. And then there was zinc and iron. When we try to heat lumps of them, nothing very much happened. They don't seem to appear to react very much. But when you powder them, you get good reactions out of them. So we tend to think of them as being a bit above copper, but maybe not just as good as magnesium and sodium. Now, the zinc, it gives us sort of blue sparks. So we drop the powder in, you get nice bluey-green sparks, so blue-green colour there. And again, the zinc powder was reacting exactly the same as all the others. Zinc plus oxygen gave us zinc oxide. And then iron, you're actually quite familiar with it, because every Halloween, if you liked sparklers, what you're really lighting are little bits of iron powder. And that orange sparks of sparklers is iron reacting. And again, it's behaving in the same way. Iron plus oxygen gives us iron oxide. So those reactions were able to give us a basic reactivity series, with sodium being our most reactive one, magnesium being a little bit less than that. Zinc and iron were next. Zinc slightly more reactive than iron. And then the one that we thought was least reactive was copper. And that's our beginning of our reactivity series. Most reactive at the top, as you go down that series, getting least reactive at the bottom. Now, why a reactivity series is useful is because you can look at what we call competition reactions. And a competition reaction is where a more reactive metal steals from a metal below it in the reactivity series. And what I'm going to do is I'm going to demonstrate 4 competition reactions. And as I go through it, I'll talk over a couple of the key observations. So in the worksheet, I've asked you to record the observations and then the word equations, and we'll talk through what the word equations are. So the first one, and this was one you did in class, it's shown in a slightly different way. So in this one, the demonstrator is going to put the mixtures. So you'll see the black powder there of copper oxide, and mixed in with that is some zinc. And they're demonstrating just how to do it. So they set a ruler just to show you about 5 or 6 centimeters of that. And then they put a flame to it, a little bit like you did. And then there it goes, it flares up. So the main observation is that flare up of the reaction. The other two observations you can make is if you look at it, you'll see there's a yellow solid. But if you look around the edges where that's cooled down a little bit, it turns white. Now, a substance that's a yellow solid when hot and cools down to white is zinc oxide. So we had zinc and copper oxide, and that's now given us zinc oxide. So the other substance must be copper. Now there's a little bit of it, you can see I'm sort of breaking the mixture up there, and you see a little bit of brown there. But quite often to demonstrate and prove that there's copper, what they do is they add a little bit of acid to it, and then that takes away things that react with the acid. Copper doesn't react with the acid, and you get to see it a little bit better. So they're going to show there that you can demonstrate that there's some copper in that mixture. So zinc and copper oxide gave us zinc oxide, that white solid, hot yellow when it was hot, now white. And then you can see there in the mixture a little bit better than you saw before, the brown colour, and that's copper. So zinc and copper oxide give us zinc oxide plus copper. So the zinc can steal oxygen away from the copper. Our second demonstration is a more spectacular one. So this is magnesium and copper oxide. So the demonstrator is going to put a gauze here on top of a tripod in a second, and that contains copper oxide, and you can see from the I think he's put there behind it, CuO is representing copper oxide, that's the symbols for it. There's some magnesium mixed in with it, and then he'll put a Bunsen flame underneath it, and the reaction takes place. Now, the reason this is a different reaction, why it behaves differently, is magnesium is much more reactive than zinc. So you'll see in a moment whenever he puts the flame in, that gives it a bit of heat. He has to step back for a few seconds, probably about 10-15 seconds before it goes off, the way he's doing it. And then you should see quite a spectacular reaction. So the heat's going into the mixture now, and keep in mind what we've got there is magnesium and copper oxide. And there's one fairly obvious observation from this. There we go. So very spectacular reaction. So the magnesium, because it's really much more reactive than the copper, it steals the oxygen away. So copper oxide plus magnesium gives us magnesium oxide plus copper. So in both of those, the more reactive metal, the zinc and the magnesium, have stolen the oxygen away from the copper. Now, the other two that we'll look at are to put carbon onto the reactivity series. So we're going to first of all see where carbon is compared to copper. So we're mixing carbon and copper oxide. Now carbon is a black solid, copper oxide is a black solid. So you'll see a mixture of two black solids are being put onto this little bottle lid. And then in a moment they will demonstrate this being put into a Bunsen flame, and then we should be able to see a reaction take place. So again, it takes a moment or two for the heat to go into it. But then once the heat goes into it, we should see a reaction. There we go. So the mixture flares up. A little bit of a flare. It's not as vigorous, obviously, as the magnesium one, but a reaction nevertheless. It did just about mix. So it would suggest that carbon isn't as reactive as magnesium, but certainly more reactive than the copper. So what would the word equation be? So copper oxide plus carbon would give us carbon oxide, which we normally call carbon dioxide, plus copper. So copper oxide plus carbon gives us carbon dioxide plus copper. And in the last wee bit here, they're just going to demonstrate that there's some copper here. And if you look at it, you'll see the brown solid, and they hover over it a wee bit better, and you can see the metallic copper there. You can see the brown of copper. So, bit of a glow. You get the brown copper, or our two observations with that one. So a bit of a glow, and then you get the copper, brown solid copper. And that's our reaction. Copper oxide plus carbon, giving us carbon dioxide plus copper. Now, what that shows us is that carbon is more reactive than copper. But we saw there it wasn't anywhere near as spectacular as magnesium was. So that would suggest that carbon is below magnesium on the reactivity series. So this demonstration proves that carbon is below magnesium. So this is from a Royal Society lecture, which they give quite often at Christmas, and they demonstrate various things. So the big box that's been brought in here, it contains carbon dioxide. You'll see there's a tripod at the bottom of it, and he's going to put some burning magnesium into that shortly. And to prove that it's carbon dioxide, you remember at the start of the year we saw that carbon dioxide is used in fire extinguishers, so it puts out fires. So he's got a bit of mineral wool soaked in petrol, and if he tries to put it inside the box, you can see the fire goes out. So that whole big box, because carbon dioxide is heavier than air, that stays inside the box and it puts the fire out. Quite likes that demonstration, so he's done it 2 or 3 times just to prove it. So the big box is basically filled with carbon dioxide. Now, he's going to show in a moment, he takes a roll of magnesium and he sets it alight. Now, when that goes into the carbon dioxide, you will get an actual reaction this time. So the magnesium is more reactive than the carbon, so it can steal oxygen away from it. So there's the roll of magnesium. And then what we'll get is magnesium and carbon dioxide, giving us magnesium oxide plus carbon. And there's the reaction. So again, you'll see that brilliant white light when magnesium reacts. So the main observation is really that brilliant white light, and there he is just demonstrating again that there's still carbon dioxide there. You'll see a lot of white powder. That's the magnesium oxide. So magnesium and carbon dioxide giving us magnesium oxide. And then the other product will be carbon, which is a black solid. So you'll see in a moment he lifts the final reaction mixture out and you'll reveal the black carbon. So magnesium plus carbon dioxide gives us magnesium oxide, that white powder forming a smoke all through that. And then when he lifts out the final mixture there, we should be able to see the black carbon. So there he's showing there's some of the white magnesium oxide, but amongst that you see the black stuff there, and that's carbon. So magnesium plus carbon dioxide, that gives us magnesium oxide plus carbon. Brilliant white light, white powder of magnesium oxide, and black solid of carbon. Okay, so what that allows us to do then is to put carbon onto a reactivity series. Now we saw it was obviously more reactive than copper, so when we go through we saw that the carbon was able to steal away the oxygen from copper, but magnesium was able to steal away from it, so it obviously goes into one of these slots. And we could do other experiments and show where it is compared there, but basically where it ends up, there's our word equations given, copper oxide and carbon giving us copper plus carbon dioxide plus magnesium giving us magnesium oxide plus carbon. So the carbon then fits in there. It fits in between zinc and magnesium. So we put it there on a reactivity series. Okay, so last little bit that I'm going to show you is a couple of videos to show a use of the competition reactions. And this is a mixture of aluminium and iron oxide. So in the first video, this is, let me turn that down. Okay, so the reaction that we saw there was aluminium reacting with iron oxide. So there's a mixture in the pot of aluminium and iron oxide, and what that's doing is the aluminium is stealing the oxygen away from the iron. So aluminium plus iron oxide is giving us aluminium oxide plus iron. Now because iron is produced and it turns out into a liquid, it basically drips out through the bottom of the reaction mixture. Now you might think, why do we do that? Why do we use that? Well, one of the places we use it is in welding. And I'll show you this video. I just muted it because I don't think we need to hear it. And just watch. And you'll see that the person here has got a big bucket that's filled with aluminium and iron oxide. And then they basically set it alight with a little bit of magnesium, and you get a very vigorous reaction. And then the molten iron runs in between the railway tracks. So it's used to weld railway tracks. And if you look over here, you'll see there's some that have already been welded. And this is basically what they're doing. They're making iron to weld together the railway tracks. So we'll see the reaction take place. So this is a little bit of magnesium to set it off. And then they stand well back. And there goes the iron. You can see it running down. It's going in between the railway tracks. And then you'll see a couple of little containers to catch any extra iron so it doesn't drip all over the tracks itself. So that's a use of competition reactions.